Hello, everyone. My name's Frank Hunleth. I'm an embedded software developer, and I'm going to show off a project that uses Erlang. This is actually quite exciting for me because I do all my work in C and C++, but Erlang fixes a lot of problems that I have with my work, and so I figured I'd try to use it. And this camera that I'm building is kind of a proof of concept to see how a lot of these ideas work, and also a way for me to exercise some framework pieces that I've been working on. So just out of curiosity, how many embedded guys are here? Like one, okay, and 1.5. All right, and then, oh, good, 2. Okay, how many guys are Arduino or Raspberry Pi or BeagleBone? Okay, good, so there are more. So, all right, so you guys will at least appreciate a little bit of this, and for the rest of you, well, you'll get hopefully I'll give you a little flavor of the embedded software development world that I tend to work on. Okay, so how's this talk going to work? So I was going to give some motivation, but it's like one of the last presentations, so I'm going to skip on the motivation to the project and then talk about a little bit how I came to try to introduce Erlang, because I really messed up bad the first time. So I wanted to at least share that experience with you guys. And other things, I'm going to go into the camera. So basically take you from the hardware to some of the software pieces, and then show you actually how it works. So while I was working on this, I collected a lot of performance metrics, but they don't really make sense unless you kind of know how the camera was built. So there's a little bit of plumbing that I was just going to go over before getting to the performance. So, all right. So, just to calibrate people, this is where this presentation's at. So it's kind of in the middle here when they're embedded Linux. It's not Arduino. That's a little bit smaller than what I work on, and it's not anything close to a cell phone. So, all right. So now that we're on the same page for what kind of embedded. So here's the start. So I want to use Erlang in a project, but no one that I know uses it, so I want to introduce it into one of my projects. Well, there's an easy way to introduce languages into projects, and that's, you build your whole C++ stuff, then you have this piece that goes with configuration scripts or some dynamic scripting part, and you put your little language there. So I know it's totally wrong to put Erlang there, but you kind of have to build comfort with these things. So okay, so I'll try to build a little comfort with it and put it in kind of the place where I normally put something like Tickle, Lua, or JavaScript. And these are, embedding these little languages in a embedded software project. This is really common. There are a lot of problems that these solve. So before you guys, I know you guys are looking at like Erlang crazy. That's using Erlang just for configuration. That's nuts, or even scripts. That's nuts. I know that's nuts. So, well, I thought, let's get a taste of it. Well, total fail. I mean, not surprisingly so. If you're working on an embedded project and you want to just try to go part way with the Erlang, I really don't think that's the route to go, because Erlang's really a systems language, and it solves the big problems. It doesn't solve these little configuration script problems that languages like Lua or Tickle are so much better at. So, all right, got that off my chest. So now we get to the camera. So I want to use it in a big way, but my problem is, well, let's give a simple project so I can get some stats and get some good comfort on using Erlang in an embedded system. So what do I pick? Well, I picked the camera because so many of my embedded projects that I work on have camera components, and this isn't the point-and-click camera. These are more like the industrial cameras that either get mounted on a vehicle or get mounted inside a manufacturing place that kind of view things. So the camera records some information. There's some processing inside the camera, and it communicates via IP. This is common setup. So let's see. So I had the idea in hand to do this, and then I wanted to make sure that when I built this wasn't like a one-off hobby. So I could just whip together a Raspberry Pi, put a camera on it, but it wouldn't really feel like something that I would throw to production. Like some of the stuff that I build, gets thousands of units at the low end, and some of the stuff that I had done in the past, it was even more. And you have to build your systems a slightly different way to support that. And I didn't want to just hack it up to get the camera to work. I wanted to have actually something that was believable, that I could produce this in more than ones and two units. So let's see. So, and of course, I was hoping to find that Erlang OTP helped me with this. So the questions, and so these are the questions that a lot of my friends and the people I'd work with have asked me. Well, we use C++, Erlang's a virtual machine. We've done virtual machines before with Java, and it was a total nightmare. So what's going to make the Erlang virtual machine better if we embed it? I mean, this goes against a lot of experience for a lot of people in the embedded field. So too much DRAM, flash memory. So it's on your PCs and on the server, to me, it seems like memory and CPU speed is just totally infinite. But on the embedded side, there's a real cost to some of these. The more devices that you make, the more pressure you have to shrink the amount of DRAM that you have because it costs more, or shrink the amount of flash memory that you use. So, and even CPU rates, there's quite a difference between like a gigahertz processor and a few hundred megahertz processor. And when you start making these in quantities, the bean counters on the project start looking at you and start saying, we need to cut costs here. Maybe you should program this in C instead of Erlang or whatever the language is, so that you don't have to use a gigahertz processor. So I wanted to make sure I had a good answer to that. Cross-compiling. So are you guys familiar with cross-compiling? So the idea is you build everything on your PC, copy it over to the place you want to run it. And for the projects that I work on, cross-compiling is really the only way we do things, because when you build the projects, if you could build the projects on the device, assuming you had enough memory or CPU, it just take forever. And when you're developing, you kind of want to have nice feedback. So to build something and hit compile, and then to be able to push it over to the device or run it on the device, you want that to take as little time as possible so that you're efficient. And let's see. Other things, I'll go quick. Well, I miss my C world. And then, of course, will I have confidence in, I guess that last one, since I'm here, you probably know the answer to that. All right. So the one constraint. So my devices are all embedded Linux, the ones I work on. And embedded Linux, if you were to draw a Venn diagram, it overlaps with a whole lot of things that Erlang does. So since this is my project and I can do what I want, I'm going to pick the Erlang way of doing something whenever I can figure out how to pick it. And and there's overlap. And this came to kind of a crazy decision that really should I have shell scripts and init scripts at the beginning. So on these embedded Linux projects, how do you start your app, right? So traditional way is to use really simple system5 init scripts, to start your programs up. And there's actually some supervision that you can get in with these init programs, and especially now with like systemd, which is another common embedded Linux tool. So Erlang does supervision, right? Of course, we can initialize stuff. So I'm just going to say no to this. Shell scripts, I guess they're not technically my enemy, but I'm going to treat them like my enemy for the purpose of this project. All right, so let's get to the camera now. And before I show it to you, I just want to give you an idea of what you're going to be looking at. So at the hardware point of view, I have a BeagleBone. This is what the BeagleBone looks like. So main thing on the BeagleBone is the big square in the middle, which is the main processor on it. It's an ARM processor. Has a couple microcontrollers in it that are really useful for hard real-time things. And when you're working on a camera, there are hard real-time things. So this is actually kind of a cool processor because of that. Other things having to do with this, well, you see the Ethernet. The programs, I'm going to store them on the micro SD card. So basically, make whatever program I have, the camera program, burn it to a micro SD card. And when I say burn, it's really just copy it, and then plug it into the BeagleBone, and then it will run the program on that processor. So that's the BeagleBone side. You buy that off the shelf. The side on the right is a board that I designed and made, and it wasn't specifically for this project, but it seemed really nice to reuse. And basically the main thing on the board is the imager. So the imager in the middle. So let's see. It's hard to see, but so the lens holder holds the lens to the camera on, and underneath it there's this little square and a little gray piece of silicon underneath it that captures the light. So that's what a raw image sensor is, and these are in all your cameras. If you unscrew the lenses to them, you'd see something similar. So I'm going to use one of those directly. Let's see. The other things on this, so that big module at the bottom is a GPS module. That's for something different. And then there are some things that you need to do to be BeagleBone friendly, and like the Cape EEPROM is one of those things. And that's really what some of the other stuff is. So you got those two boards, and you stick them together because they plug in nicely here. And then here, this next slide, kind of show you how they connect wire-wise. So the big piece is the main processor on the BeagleBone. That's the AM3359. Told you it had the ARM piece that's embedded. So it has also other pieces inside this big chip. The interesting one is this programmable real-time unit. And this is kind of like a little microcontroller, like an Arduino, that's just built in, except it runs really fast. It's 200 megahertz. And the cool thing is that when you program it, they make it very easy to be hard real-time. So Erlang is soft real-time, but this is hard real-time, and it will hit your deadlines as long as it has enough cycles to hit them. So I have connected the imager into the PRU microcontroller. So basically just connected the wires. So the imager, what it outputs, has data lines. So when it reads out what image it sees, it starts at the upper left-hand corner and just goes raster order, and each pixel is 10 bits. So there are 10 lines. Now for this demo, I chopped off a couple bits because, well, 10 bits is not useful for displaying on PC monitors, which don't do 10 bits, or for pretty much compressing, because most stuff doesn't do 10 bits easily. So anyway, so the data comes in there. There are a couple other wires to handle the synchronization, and that's the pixel clock and horizontal sync and vsync. And basically all that is you read off the rectangle, and these wires go high or low at different points when it's reading out all the pixels in this rectangle to send back. Other pieces, I2C master, so I2C is common bus. BeagleBone has hardware acceleration, so that goes there. You can control things in the imager, exposure times. There are different curves that lighting curves that you can have on the imager. And this is actually kind of why you use a raw imager rather than a webcam. It's to get access to all these cool things, cool features that you can get to if you have the raw imager rather than somebody's little piece of firmware that connects to a raw imager. And lastly, GPIO, there's a reset line. So the reason I put this out is because Erlang's going to supervise hardware here. So hardware misbehaves, reset line goes high, and the imager reboots. So hardware needs supervision as well, and it does the same thing. All right, so that's kind of the hardware pieces. So I want to walk through how the software is basically put together, but I'm really going to focus on the streaming part because the other parts are possibly less interesting because it's more glue kind of code. So left side, Erlang, right side, PRU, the hard real time. So I use Cowboy. So what we're going to do is we're going to stream video over to a web browser, right? So we use Cowboy. And I have a couple handlers on this. So the static one, of course, so I can serve my web page material over when the browser requests it. The interesting one is the streaming video handler, and I'm going to get to that in the next slide. And then there's also a little WebSocket so that you can kind of control and tweak things on the camera. So on the video side and the control side, that all goes to a gen server, which acts as the camera interface. That server talks to, the key part is it talks to a C external port. And I think before one of the talks yesterday, I thought that everyone did external ports and very few people did NIFs. But now I realize that's the opposite. Well, for this project, I do only external ports, not linked in. And the reason is that part of the reason for Erlang is for the robustness. And if I start linking in too much of this crazy code, then I will defeat the purpose. And it's actually one of the things that makes Erlang really interesting to me is the fact that that you can achieve this process isolation. So now the question is this going to affect performance? Well, we'll get to that. So anyway, there's a little frame capture process, and it talks to the PRU. So the PRU basically gets a frame in, starts writing it to memory, sends an interrupt over. The frame capture C code says, OK, I got a frame, copies and sends it back to Erlang. And it keeps on shoving frames over as they come in from the real-time side. One thing that I do, so I hadn't mentioned this before, was, well, how do I stream the video to the browser? The way I chose for this project was to use Motion JPEG. Motion JPEG is awesome because it works with every browser, and it's really easy. It's less awesome in that you're not going to be streaming movies over the internet because there's a bandwidth cost. But you don't have too many choices with the BeagleBone because there's not hardware acceleration on it to do the encoding, which is really what you need if you want to build this project right. But this will work. This will work fine. And there's a library called libjpeg turbo, which will take care of that. And I stuck that in the port side because I'm going to compress every frame, so might as well do it there. The other pieces, I use Erlang AL for the GPIO and I2C access, and that actually worked out quite nicely. I had to make a few modifications for the BeagleBone because their default platform is Raspberry Pi, but hopefully that will be changing as I get to contribute some of this work back. All right, so Motion JPEG streaming. This is how it works. Client sends a request. You get a multi-part reply, and each of the images is a frame that the browser will just display it. And this does work, believe it or not. It's as simple as it is. Didn't quite know this going into when I built this, that it would be quite this easy to do Motion JPEG. And actually, this at one point in time when I discovered that I could do this, I was almost embarrassed because I thought, man, I had this great idea for showing a whole streaming stack. I thought I was going to write all this Erlang code, and it'd be so cool that I could show all these guys that how cool Erlang was, and we're streaming and doing Motion JPEG, and then that was it. And so this is all the code I wrote, and at one level, I was kind of sad because I thought I'd show you guys something super cool, and then another level, well, this is super cool. I mean, I've never written any streaming code that's an order of magnitude this small. So I'm gonna just walk through how this works. So Cowboy calls the handle when this request come in. I didn't show a lot of the Cowboy stuff going on, but from the previous slide, the first thing that gets sent is the header, the multi-part header, and you can kind of see it being built up. Cowboy gets called back to say that there's going to be a part reply. There's something special I have to do for the first picture, which was kind of sad. It's essentially the same as the subsequent pictures. So I just showed this. So for all the pictures, what you do is you call into this camera interface and just get next picture. So get next picture in the camera interface basically just waits, blocks, and then when the next picture comes in, it returns. And if you have if you're serving multiple clients, they'll all block, and then they'll all get woken up when the next picture comes in. So easy as that. And get the picture, build the message that you're going to send back, and send it, and then call back. And it continues. And this works amazingly well, and due to Erlang's let it crash, when the client disconnects at any point or time or anything happens, it cleans itself up. Everything's good. So, all right. So just so you guys believe me, let's try to get to the demo. So let's see. So this is the camera right here. So the first part. So what I have right here is I have the Ethernet connect up. See, there's power. And then this line, this is the console. So it will boot to Erlang. And you wouldn't normally have the console on here, but I thought it was kind of cool to show what this thing looks like. So I left the cable connected. So let's power up. So I'm plugging the USB. USB provides power, so it's 5 volts. So okay, there, powered up, and now we have Erlang shell. Did you guys see it power up? Okay, so then let me move over to here, and let's see if I hit reload. Okay, here, there. All right. Oops. There you guys go. All right. So this is running at 45, and so it should hopefully it doesn't have that much latency. Hey. All right, and I'll leave this up. So I'm going to go on to the rest of the slides. But as you can see, it works, and maybe I need to focus a little bit better. But it's there, and so let me go into some of how it was built. All right, so that's the demo. Okay, next part is the plumbing. So I really wanted to give you stats on how this all works, but it totally doesn't make sense unless I tell you a little bit about how it's put together and a little bit more about the project that I've been working on. So the project that I've been working on is called Nerves, the Nerves project, and the idea is it's a project to make cross-compiling with Erlang and building these images as easy as possible. So this is basically how it works. So there's 2 paths. There's this top path and the bottom path, and the top's the Erlang side, and the bottom's the C and C++ side. So it's almost the same as what most people typically do with the Erlang program. So you write your code, you type it in, you run rebar, or I support Erlang.make almost. It's in a branch right now, and I'll get to that. So that compiles everything, or cross-compiles. So if you have a C port, I set up the environment, so invoke the cross-compiler and do the right thing. So once you get that, then you run relax on it, and that will create a release. And this was one of the coolest things when I got started with Erlang to find out was that the process to build the release automatically trimmed out all the cruft, all the stuff not cruft, but all the stuff I don't use in the main Erlang distribution, which is quite sizable, and it packages up really nice. So then you have your release on that top side. Then on the bottom side, you need the Linux kernel, your bootloaders, cross compilers, all that stuff to make this work. So I used a project called BuildRoot, and this is a typical embedded Linux tool that people use to create these systems. So it consists of these makefiles, and it's really nice. If you want a library, it has little menus, and you just pick the library. If you want a specific Linux kernel, you pick the Linux kernel, and it saves it to a nice config file. So I customized it to be specific to Erlang and to build images that really the focus was on Erlang and not really on, and less so on embedded Linux. So when you get Nerves, you get this BuildRoot customization, and it builds what I call a base firmware image. So this is a blob that has the kernel, bootloaders, and everything, but doesn't have your Erlang program in it yet. So that's added at the firmware tool. That steps, you see how it kind of combines. There's a little script that merges the RelX created release and merges it with this base firmware image. And then the output is a SD card image, and that you can copy on. I also create a little firmware update file. So the difference between the two is that the SD card image is something that you would program the first time, or you give to your manufacturing plant, because when they build all your devices, they like to take your memory chips before they put them on the side of them on the board and program them in mass. So you need to give them the image. So that's that piece. The firmware update package is a little zip file that contains instructions for how to how to update firmware on device. So this is update the Linux kernel, for example, and other things. So this will you distribute, to end users or to test team and whatnot. So there's that part. I also have another piece which I built while I was working on this, which was to somehow be able to update the target image a little bit quicker than burning the SD card. I mean, burning the SD card really only takes about 10 seconds, but you kind of have to unplug, plug, and all this, and it's really annoying. So I wrote a little tool called Rsync, and I'll talk a little bit more of this, but basically the idea is it pushes your new updates over to the board so you can test them without doing all this manipulation. You can get feedback quickly. All right, so what does the raw SD card image look like? And this is a blow up. So disks, floppy disks, hard disks, all this, everything looks kind of the same. It's the same thing for on the embedded side. You have master boot record. On embedded, we're a little bit old style. We don't do the new style partitions but we have the master boot record from the DOS era, and then you have your partitions. And the way I set this up is I have two. So when you run this, you load Linux and you load the tools off of one root file systems. I keep 2 copies on here, and so when the camera boots or when you boot, you run off the first one. Let's say you run off file system A. When you update it in place, writing to yourself while you're running doesn't necessarily work unless you try at it. So I don't try. I just, when you want to do a firmware update, I write the second one and then reboot to run the second one. Then you boot back. When you bounce back if you want to update it again. So that's the idea. I did make so the other part is where's application write data. I have a special partition for that. And there's kind of a logic here. With the embedded devices, you really don't want to screw up the root file system because the people using it don't really have recovery tools. You screw up the root file system, the thing doesn't boot maybe, or it does something funny. I mean, if your file system gets corrupt on your hard disk, that's not good, but there are tools to fix it, and a lot of people put a lot of effort to make desktops to give desktop users help with this. But embedded is not that way. So I keep my file systems read-only so to minimize the possibility of messing them up. That makes development a little bit trickier, but you can work around it pretty easily. So just when these things get burnt, just you boot up with a file system. It's read-only. Someone pulls the power, fine. Nothing lost. It's read-only. Updates go to a different partition. Everything's fine. The system. I try to make it hard to corrupt, and this is typically what embedded people do, as long as they have enough flash space to have a copy of the root file system. All right, so this is what I was getting to. Reprogramming SD cards really begins to suck. I know I told you it's only like 10 seconds to program these things, but you have to move your hands, and it's just a total pain. So I found a tool. So there's this sync tool by Rusty Clubhouse, and I was just like, oh, this is so close. When you hit save in your editor, save a file, it notices the change, pushes, updates the Erlang, loads your new module into Erlang, and you can go. But it wasn't quite good enough. So I basically took his idea and made a little command line tool called Rsync, which is essentially Rsync, except it communicates over the Erlang distribution protocol to take whatever was created by RelX and just copy it over to the place where your Erlang beam files are on the target, and then notices, okay, I copied this beam file over because it changed. I better reload the module. So it does that. The other thing that I had to do is I added a little script so you could have pre and post update scripts to stop and start applications, and this was useful because if you have an external C port, right, and you want to update it, so now you're updating C code, if that port's in use, you get an error because you can't write to it, so not good. So, but if you shut down the camera interface, it will shut down the port. You can write to the file, then you start it up again, and everything works. Let's see. Let's see, okay, so the limitations, you must have a writable file system, of course, but you can easily get around this. You use a union file system. So you guys familiar with union file systems? Okay, so you have a base one, say it's read-only. People do this on like CD-ROMs if you want to boot Linux off of a CD-ROM. So it's read-only by necessity. And then you can have this other file system that gets mounted on top. And if you try to open a file and it's not on the first one, the one that's mounted on top, the writable one, then it goes to the one underneath. And it's really nice and easy to do. So I do it, and that's basically how you develop. And then if you mess up your code and you totally host the board, you reboot, and everything that you wrote to the union file system is gone. It just disappears. It boots. It's your old code, but it works and it boots. So you don't have to open up the case and get at it. Okay, let's see. NIFs and LinkedIn port drivers. I think I have a way to get around this, but when I first was doing it, I was crashing the VM, which is kind of crazy because you don't crash it immediately. You crash it midway through running your application somewhere down the line. So it's a little weird to debug. All right, so last thing before we get to stats, and that's booting to Erlang. So we have a little program called ErlangNet. So when you boot Linux, process 1 is init. Process 1 is now ErlangNet on this device. And it basically does what your start scripts do for running any Erlang application, except it does it in a little bit of C code, and it also initializes some other system stuff that is just system environment stuff that you just have to have initialized to run Erlang because, Erlang expects to have the system in a nice setup state, not the raw one that you get when the kernel just moves to user land. So let's see. Yep. So that's that. All right. Performance. So throughput. 45 frames a second. Why 45? Well, I had a clock on the imager, which happened to divide evenly to 45 frames a second. And rather than muck with it, I kept it because, I think I could get up to 60, but 45 was a good place, and it was really easy. And then, I didn't update it because I connected to this to measure the frame rate that I was getting to check that I was actually getting 45 at the browser, and I wasn't. I was getting 43 and a half. So I said, about 1 frame drop per second. Okay, so 1 or 2 frames dropped every second. So I was just like, what's going on? How am I dropping? So it was JPEG encoding, which was crazy. So after all this, the JPEG encoder happened to take almost exactly 22 milliseconds, which was unbelievable. In fact, I didn't believe it when I first found it because the fact that it would take almost exactly my frame rate was just something that I just didn't expect it. So I kept on taking it out, and sure enough, the JPEG encode time actually did take almost exactly the frame rate, and that was the cause of this drop. But the JPEG encoder's in C, so Erlang's safe. So at least for throughput. All right, so the next thing that you might want to know is latency, right? So something changes in the world. How long does that take to propagate to over through the camera, over the network to the PC? And the way that you typically do this is you shine a bright light at the camera, maybe saturate or something like that. Hook up a logic analyzer so you can have the exact time that light goes off, and then I have some other wire come out that triggers exactly when the packet comes in. Then you get on your logic analyzer a nice distance that you can use to calculate latency. But that's less cool. And I had one of these 7-segment displays sitting around, so I figured I'll hook this up. So how this works is I show a timestamp on this. So this is like a $20 SparkFun 7-segment display, and it's connected. This is actually serial, so it's connected up, and it basically counts. So this is the first 1 seconds, and then the next 3 digits that's milliseconds. So it keeps on counting. Shine the camera on it, then the camera's taking pictures of it, and I log the timestamp of the picture when it comes in, right? So then I have that timestamp, and I can see what the picture looks like, and it can tell me, I can subtract and figure out the time, and I can do this for a bunch of pictures and basically get an idea of the latency. So here's another way of looking at how it's set up. So I just had to write a little application. Used Erlang serial, which is an interesting library because if anyone uses serial ports, this one's been forked many times. You need to find the right port and then it will work for you. So connected up, and there's a little app, and then of course it connects to the camera over HTTP and saves these timestamp files, and you get a picture that looks like that. So you can see it says 410 on it. The timestamp. So sadly, you can't see the timestamp because it's in the file name. So I just wrote it up there. So 481. So you just subtract, and that one happened to be a 71 millisecond frame. All right. So 71 milliseconds, is that good, bad? All right. So the way you figure this out is you break up all the components that can add latency. So that's basically what I did. I said, okay, how much latency can I account for in the system? And this is really easy to account for some latency. I mean, updating the displays, because of how I had implemented, I wasn't being super accurate with that. So I knew I had some in there. There's exposure time on the camera, right? It's not like these cameras expose instantaneously. The imager that's connected, you have this big parallel bus, but it doesn't go all that fast. So that actually takes quite a long time, and I could probably ramp up the clock a little bit, but it's around 20 milliseconds for what I got there. And then of course we found out JPEG encodes 23. So that's really easy accounting there. And I get, in the 50s, about 60 milliseconds. So the remaining latencies is 12 to 30 milliseconds, which actually from my experience, this is around what these things kind of end up when you implement them like I did. And this is nothing to pick on Erlang. It's just how the system's architected. There are ways of building these things where you can really cut down the latency. But this is quite reasonable to expect. And Erlang it's totally not a problem on this. All right, so let's see. Boot time, another interesting stat, maybe less interesting because once it's booted, it's not supposed to reboot. But when you're building handheld devices or stuff with user interfaces that power up, people don't like to wait. So this shows you the breakdown. So these are the bootloaders, Linux. So you see Linux takes you all the way out past 2 seconds, and some of that's just an aspect of loading data off this SD card. And then we get to Erlang. And Erlang's the interesting part because I had one big score for Erlang. So basically, when do I start Erlang, and when does my app, when can I start streaming from my app? So I had that one, but I really wanted to get a little bit more granularity so I could pick on components of Erlang. And this was non-trivial. So I wanted to explain what I did so you could understand this. So starting Erlang VM, what does that mean? So how many of you are familiar with the simple execution environment in Armstrong's Erlang book? So basically what he did, and this is in the appendix, he said, okay, can I run Erlang without the kernel, the kernel application or standard lib? So just totally bare. And he writes hello world in this. So it's just like, okay, what if I take what he did and run on here? How fast does it boot? Well, it boots that fast. It boots in 270 milliseconds on the BeagleBone. Totally bare, hello world. So I said, well, that's the starting the VM part because it can't be doing much else. The next question was, well, how long does it take to load everything besides my app? So I just timed the amount of time it took to get to the Erlang prompt, for lack of a better measuring place. And that was this next group. So basically it's 1.37 seconds additional to get to that on this chip. And then, okay, the last part is, what's the remainder? The remainder is obviously my fault with how I wrote my Erlang code, and that's that. But I think the summary from this is that this is not that long. We could improve this, but it's probably not worth trying too hard unless you have an application that really needs to boot quick. All right, so another problem, DRAM usage. Big deal for embedded. I mean, I guess big deal for you server guys as well. So, but these devices stay up for a long time. And if it runs out of DRAM, and our DRAM limitations are very small, we don't have swap, then bad things happen. Usually the device slows down some random way, and people start complaining, and it's actually kind of hard to debug. So I said, well, how long does it take? What's my DRAM usage? So for this device, connect, stream, disconnect, connect, stream, disconnect. That's basically exercising the device it's about as much as you could exercise the code that's on it. And after a half hour, it basically reaches steady state. I actually left it going, but it's totally uninteresting. It's 28 meg the entire way, and this is okay. So this is more than Erlang. This is Linux kernel, everything growing, and I don't want to underscore this. This is actually kind of cool. I didn't do anything. It just worked, and this doesn't just work in my experience. So that was nice. Okay, so the next one was, well, how big is it? Do I have to have a big SD card? Well, it's just that root file system is 18 megabytes total, and the split. So basically, this bottom one, you kind of see it's basically a 60-40 split for Erlang on the right, the 40%, and the other stuff on the left, the 60%. So I don't know if you can read the numbers, but I use the ext4 file system because it's fast, even though it's read-only. It just happens to be amazingly optimized in Linux. So if you don't mind burning some flash space, you actually get a performance boost. So I just use that. But you can see it actually, there's a little bit of overhead. C libraries. Let's see, on the Erlang side, not quite sure this is going to be surprising for you guys, but the standard library and kernel, of course, are quite large compared to most of the other stuff that you pull in. But in the end, I use Qt, the Qt framework in C++, and I'm looking at the exact same numbers for Qt. Now, Qt does GUIs, and I didn't pull in GUIs, but a lot of people use Qt for the networking stack and a whole lot of system abstractions when they build their embedded devices. So they're pulling in a lot of this stuff, and this is completely on par. This is not going to surprise most people using who are building embedded Linux plus Qt on the C++ side. So anyway, that was the performance I found. So basically, getting back to the questions I wanted to answer, and it's positive. Is Erlang too slow? No. I mean, my problem was the JPEG compression. I mean, I'm using external ports, so I'm not doing stuff as efficiently as a lot of the other talks that I've been here. So I'm feeling kind of good because I have some knobs to turn. Although I probably would keep things separate just for this robustness. DRAM flash, we just saw that. Cross-compile, this actually turned out to be nicer. Once I got Rsync working, then it got to be a lot more enjoyable. Unplugging and plugging the SD cards got old, even though I could just program them in a couple seconds. And also, if you do that too much, you'll break the SD card programmer because you'll wire out the slot. Well, you'll get to that if you do that. Let's see. Libraries, frameworks. Cowboy is awesome. I mean, all right, so granted, I'm coming from C++, and maybe my bar is beyond low, but this was by far the easiest I've ever done any web stuff, like ever, in my life, and this was actually quite a bit of fun. So no, I don't miss it. So do I have confidence? Yeah, I actually have quite a bit of confidence, and I have some metrics that I hope can help sway others that using Erlang for embedded is not exactly a crazy thing to do, and I think you get a lot of benefit out of it. So let's see. Just if you guys are interested in any of this work, it's all on GitHub. So I've posted all. Most of it is under the NERSC project, and I'll try to get you started to run on the BeagleBone. So BeagleBone's the first one. There's really nothing keeping it from working on like Raspberry Pi or that, other than I just haven't done it. So if you are a Raspberry Pi person or something, or have some other platform, it's probably not too hard to port, assuming build root already supports it. So let's see. So there's that. Then where's nerfs going? Well, I finally got the nerfs up to where there are a couple actually real projects that are trying to use this. So hopefully we can take it the rest of the way and actually get some real use out of this, because that's kind of the point. Documentation, if you don't see something, probably just email me. I have a lot of stuff there that's not visible, so I'm going to try to fix that. Networking configuration, so once you get this static IP, there's some stuff that would be prettied up. And since I'm using embedded Linux on this, the tools exist. They're easy to get to, but you may not know how to like set up Wi-Fi. But you can set up Wi-Fi, and it works. It's just you're just operating at a slightly lower level. And Elixir. Don't want to forget this, because Garth Hitchens, I just want to point him out. He just got some Elixir working on this. So now you can start booting to Elixir on the board, which is going to be quite a bit of fun, for me at least. So there's where to go, and that's my talk. So thanks for coming, and if you have any questions, feel free to ask me, or if we ran out of time, I'll be around.